welcome to another video on some topics in topology. In this video we mainly we discuss the generalizations of the concept like cluster point and limit point. Okay, and these concepts we are going to generalize in the with the help of the concept of filter. See, first of all, we require some definitions. See, if script f and script g are two filters on the same set x. See, we have a set x and two filters are there given. F and G, script F and script G be two filters on a set X, then we say that F is finer than G. F is finer than G, provided that G is a subset of F. If all filters present in if all members of G are members of F, then we say that F is finer than C. F is then finer than G. And we also describe this situation by saying that G is coarser than F. G is coarser than F. Okay, the motivation to motivate our intuition here, because all filters are closed under supersets. See, all filters contain the larger sets. So see, all filters contain the larger sets, and when a filter is finer than another, then it must contain more small sets. So when a filter is finer than another, then it must contain more small sets, and therefore so when F is finer than G, then it contains more small sets compared to G. See, another definition: a filter F on a set X is called a fixed filter. A filter F is called a fixed filter if there exists a point X in X with X an element of intersection of F. So it is called a fixed filter if there exists a point X in X. If X is a point X such that X an element of X is an element of intersection of F. A filter which is not fixed is called free. A filter which is not fixed is called a free filter. So that is, F is a free filter provided the intersection of F is equal to the empty set. And the neighborhood filters are always fixed. See, the neighborhood filters are always fixed, and because X is present in the intersection as that member, which as the member of X, capital X. Okay. It takes a moment to convince yourself that free filters can even exist. See, free filters can even exist, but the following example is a useful one. Example. See, it is called the Freshet filter. So let C equal to the set A infinity, the open set A infinity where A is an element of R. It is obvious that C is a filter based on R. Then C is a filter based on R. Then the filter F generated by this filter base is called the Freshet filter. Notice that the Freshet filter is a free filter on the real numbers, on the set of real numbers. So this example provides this case provides us an example for for free filters. For example, as an example for a fixed filter, every the filter generated by the neighborhood base of any point is sufficient. Okay. Now another example. Suppose A is a subset of X and A is not equal to the empty set. If A is a subset of X and A is not equal to the empty set, then the collection FA, F subscript A is equal to F subset of X such that A is a subset of F. A subset of F is a fixed filter. Then it is a fixed filter. Example for a fixed filter, not a free filter. And notice that FA is finer than FA is finer than FB if and only if A is a subset of B. Okay. Next definition: Suppose f is a filter on a topological space X and X an element of X. If f is a filter on a topological space X and X an element of X, then we say that f converges to the point X, convergence of the filter. Then f converges to the point, converges to X, or X is the limit point of f. In other words, X is the limit point of f. If and only if ux is a subset of f. If and only if ux, that is the filter, the neighborhood base at the point X. If and only if the neighborhood base ux at the point X is a subset of f. In this case, we write that f converges to X. So okay, thus we define convergence and limit point and existence of limit point for a filter f with only with the help of the neighborhood bases. Last definition here. The definition says that suppose f is a filter on a topological space X and a point X is in X, and we say that f clusters at the X. The filter f clusters at X, or X is a cluster point of f. F clusters at X, or X is a cluster point of f, if and only if X is an element of intersection of closure of f, intersection of closure of f, such that f is is an element of f. So if X is a member of the intersection of closure of f, where f is where here we consider all members of script f. Okay, these are the definitions that we require to proceed to the next result. On some results are there to follow, are here to follow. Okay.